Today we're gonna build a motor effect. All we need is masking tape, a 1.5 volt battery, a ceramic bar magnet, copper wire, and sandpaper. So let's get started. So first, we cut a 1 meter piece of copper wire. And using sandpaper, we remove the insulation from both ends of the wire just to increase conductivity. So we're just going to rub the ends. After removing the insulation, you can see that the edges of the wire are dimmer than the rest of the copper. This means it's ready to go. So now we're going to take our 1.5 volt battery and we're going to tape it to the table. Try to tape it close to the edge of the table. You're just going to grab a piece of masking tape and make sure the battery is secured to the table. You're going to take the wire that you already removed the insulation from and you're going to tape the edges of the wire next to the different sides of the battery. So one side is going to be close to the positive side of the battery and you're going to tape the wire. Make sure you leave part of the wire hanging here close to the side of the battery and you're going to do the same thing with the other side of the wire. So here you can see that the loop of the wire is going to be hanging down the table and the wires are going to be close to the different sides of the battery. Right now the positive side of the battery is on the right side and the negative side is on the left side. So now what we're going to do is we're going to plug in each wire onto the respective side of the battery to create a current. So now that we have the wires on each side, we can predict that the current is always going to flow from positive to negative. So on this side of the loop, the current is going down and then it's going to turn towards the left side and it goes up again. So now if we put a magnet at the bottom of the loop, let's see what happens. We can see there's a force that's pushing the loop inwards. So right now, in this scenario, remember we have the positive side on the left side and the negative side on the right side. We know that current is always going to flow from positive to negative. So at the bottom of the loop, we see that the current is going to point from left to right. Remember we have a magnet here, so we're interested in knowing what the direction of the B field is on this side of the loop. So now using right hand rule 1, we can figure out what the direction of this B field is. So we're going to use our thumb to point in the direction of the current and then we're going to curl our fingers into the direction of the magnet. So we see that if we curl them, the B field is going to point down. So now, using right hand rule 2, we can explain why the loop is actually pushing in when the magnet is placed and there's a current flowing through the wire. So our thumb is going to point in the direction of the current, our index finger is going to point in the direction of the B field, and our middle finger is going to determine where the magnetic force is pointing to. So current, B field, and we see that our middle finger is actually pointing in, which explains why the loop is actually going inwards. When we flip the battery so that the positive side is now on the right side. As we flipped the battery, it means that the current switched directions. So now the current is going to go in the opposite direction. So let's see what happens if we place a magnet at the bottom of the loop. We can see there's a force that's now attracting the loop into the magnet. So in this scenario, our battery, the positive side is now on the right side and our negative side is on the left side. So the conditions from the previous scenario are inverted in this situation. So now, remember that the current is going to flow from positive to negative. So now we know that at the bottom of the loop, so we go from positive to negative, it's going to flow from right to left. So now, just as we did in the previous situation, our thumb is going to point in the direction of current And now we're gonna see that even if the current is flowing in the opposite direction, our B field is still gonna be pointing down. But now we see that our force using right hand rule 2 is now pointing outwards, which is why when the magnet is placed next to the loop is actually being pushed outwards towards the magnet.
In this experiment, I will be demonstrating Lenz's law with grapes, a straw, string, and magnet. When you bring the magnet toward the grape, you induce an electric current in the atoms of the grape that make them magnetic in a way that will repel the approaching magnet. This is the same result as predicted by Lenz's law. When you move a magnet toward an electrical conductor, it will create electric currents in the conductor, turning it into an electromagnet that repels the magnet. Grapes can repel the magnet because they are mostly made of water, and water is conductive, which is why it can do this.
So for this experiment, we just used a battery, copper wire, and a magnet to demonstrate the Lorentz force, which is the combination of electric and magnetic force on a point charge due to electromagnetic fields. So basically, if a charge moves with velocity in the presence of an electric field and a magnetic field, it will experience the Lorentz force. And this is what it looks like. As you can see, we have built a simple motor using the Lorentz force. In the demo, the copper wire connects the positive terminal to the magnet at the negative terminal, and this completes the circuit. Therefore, a current is flowing through the wire. And since the battery is attached to the magnet at the bottom, there is a magnetic field present, so the current is actually flowing in the magnetic field. And when this current flows in the magnetic field, it'll experience a force called the Lorentz force. And this acts perpendicular to both the current's direction and the direction of the magnetic field. This force is what causes the wire to spin in a circle, as you saw in the demo. Here's a diagram of what is happening in this circuit. So the current flows downward in both wires from positive to negative. And using right hand rule 1, we find that the magnetic field is pointing outwards when it reaches the wires on the side. Then using right hand rule 2, we find that the force points into the page on the left side and out of the page on the right side, causing the wire to rotate.